Two coffee shops, identical in every way. One is busy half the time. The other is busy 90% of the time. A well-run, popular shop. Nothing pathological. At the first shop, your average wait is about 1 service time. Quick. At the second, 9 service times. Not 10% worse. Not twice as bad. 9 times. Push the busy shop to 95% and the wait doubles again. 19. No one is slacking. The machine isn't broken. This is the mathematics of queues. A cliff hidden inside one innocent fraction, and it runs every line you have ever hated. The minimal model, honest and bare. Customers arrive at random, independent, memoryless like raindrops. One server, service times random 2. First come, first served. 2 numbers rule everything. The arrival rate lambda and the service rate mu. Their ratio, lambda over mu, is the utilization, rho, the fraction of time the server is busy. Rho is the dial we will turn. Everything that follows the cliff, the fixes, the design rules is the story of what rho does to waiting. Intuition says utilization is efficiency. A server busy 50% of the time, half wasted. 90% busy, excellent management. Factories once chased exactly this. Keep every machine grinding. But watch what the busy fraction hides. At rho equals 0.9, the server is idle 6 minutes every hour. Yet those minutes never arrive when the crowd does. Randomness clusters. Arrivals bunch up. The idle time is real but useless because it comes in the wrong moments. Efficiency for the server is not efficiency for you. Now the cliff computed honestly. We simulated hundreds of thousands of customers at each load level. Rho 0.5, average queue wait 1 service time. Theory says 1. Match. Rho 0.8, 4. Theory 4. Rho 0.9, 9. 0.95, 19. The formula behind the curve is tiny. Waiting equals rho over 1 minus rho. That denominator is the villain. As rho approaches 1, 1 minus rho approaches 0, and the weight divides by almost nothing. The last 10% of utilization doesn't cost 10% more waiting. It costs everything. Here is the twist most people never hear. Load alone does not create waiting. Run the same system at 90% load, but with perfectly regular arrivals, 1 every 10 minutes exactly, each service exactly 9 minutes. The wait is 0. Forever. Nobody queues. Same load. No randomness. No waiting. Queues are not made of work. They are made of variability. Bunched arrivals, occasional slow jobs, that is the raw material of every line. Load only amplifies it. 1 minus rho in the denominator turns small fluctuations into long waits. One law survives every complication. Little's law, L equals lambda W. People in the system equals arrival rate times time in the system. No assumptions about randomness, discipline, or the number of servers. It holds for coffee shops, hospitals, factories, and web servers alike. Our simulation, Measured occupancy 8.86. Arrival rate times measured wait 8.87. The law closes to 0.1%. It is the accountant of queuing. Count any two of the three, and the third is determined. Managers measure queue length by timing waits, and vice versa, because of this one line. Now the design lever that feels like magic. 2 clerks. Option 1, 2 separate lines, customers pick one and stay. Option 2, 1 shared serpentine line, next customer to whichever clerk frees up. Same clerks, same customers, same work. We simulated both at heavy load. Separate lines, average weight 8.6. 1 shared line 4.2. Twice as fast from geometry alone. Pooling works because it never lets a clerk stand idle while anyone waits. The wasted idle moments get recycled. Banks, airports, and hospitals switched to the single snake line because arithmetic, not fashion, said so. And the eternal grievance: why does the other line always move faster? Partly it truly does. In separate lines, randomness strikes unevenly. One slow customer freezes your lane while the neighbors glide. Partly it's bookkeeping bias. With 3 lines, your line is fastest only one time in 3, so 2/3 of your supermarket memories are of losing. The fix is the previous scene. Pool the lines, and there is no other line to envy at all. The grievance is real and solvable. The field has a birthplace, Copenhagen, 1909. Agner Krarup Erlang, an engineer at the telephone exchange, asks, how many lines must we build so callers rarely hear a busy signal? Too few, constant blocking. Too many, copper and money wasted. Erlang derived the formulas that balance the two, still used, unchanged, to size call centers and cell towers today. The unit of telephone traffic is named the Erlang in his honor. Every your call is important to us is a queuing formula holding the line. The design rules fall out of the cliff. Rule 1, never run hot. Cloud operators target 70%. The last 30% of capacity is not spare. It is the shock absorber. Rule 2, fight variability, not just load appointment systems, triage. Standardized tasks all flatten the spikes. Rule 3, pool whenever fairness allows, one line, many servers. Rule 4, measure with Little's law, 2 numbers give you the third for free. Emergency rooms, kitchen pass-throughs, airport security, your laptop's task scheduler. All the same 4 rules, all the same little fraction. One formula ties the whole story together. Kingman's approximation, 1961. The weight is a product of 3 factors. A variability term, how bumpy arrivals and services are. A utilization term, rho over 1 minus rho, our cliff. And the bare service time. Weight equals variability, times congestion, times duration. 3 knobs, 3 strategies. Smooth the bumps, back off the cliff, or speed the service. Every queue management trick ever invented is one of these 3 knobs in disguise. One fraction, rho over 1 minus rho. A cliff at full utilization, a weight made of randomness, an accountant named Little, and a snake line that halves the pain. Fully utilized is another name for about to collapse in checkout lines, phone networks, hospitals, and servers alike. The mathematics of waiting is not about patience. It is about design, and the design was published before your grandparents were born. The line is long because the idle minutes came at the wrong time.